Like in monoprotic acid and bases, purpose are possible for diprotic acid and bases. But in this case, we can make purpose in two different pH ranges. Okay, for diprotic acid, three species are present depending on pH. Okay, H2A, HA minus, and A2 minus. Okay, so by combining these two, okay, we have two buffers. Okay, first buffer is made out of H2A and HA minus. Okay, applying Henderson-Hasselbalch equation, we can write this equation. Okay, pH1 equals pK1 plus log this ratio. Okay, and also using HA minus and A2 minus, we have another buffer, okay, which is pH2 equals pK2 plus log, okay, the ratio of these two species. All right, but using H2A and A2 minus, it's not possible to make a buffer. Okay. Okay, let's take a look in detail. Right. Um, let's see. Let's consider KHP. Okay. Find the pH of a solution prepared by dissolving 1 gram of KHP plus 1.20 gram of sodium phthaleate. Okay. Well, this one KHP, when it is dissolved in water, it is completely dissociates like this one, and this sodium phthaleate, when it dissolved, it is also completely dissolved, leaving this phthalate ion in solution. Right. So in this case, what there are three, one, two, three different species, but in this case we have these two. Okay, hydrogen phthalate and phthalate. Okay, and using this one, and we use in this case pK2. Okay, so pH equals pK2, which is 5.408 plus log, and this the ratio of these two the concentrations. Okay, since the volume is the same, we take a ratio, a mole ratio. Okay, this phthalate, mole of phthalate is what? Sodium phthalates. Formula mass is 210.994. Okay, so 1.2 gram is the mole of this one is given by this one, and this one hydrogen phthalate, and the KHP formula mass is this one, 204.221. Okay, and we have we calculate the moles, and then we got pH of 5.47. all right, yeah, this is very simple. Okay, and okay, let's look at another example, preparing a buffer in a diprotic system. How many this question is very important but a little bit complicated. Okay, so follow me. Okay. How many milliliters of 0.800 molar KOH should be added to 3.38 gram of oxalic acid to give a pH of 4.4 when diluted to 500 milliliters? Okay, it seems quite complicated. Okay, here oxalic acid structure is like that. Okay, so the oxalic acid form, it is diprotic acid because 1 and 2, there are two protons to be dissociated. Okay, so it undergoes dissociation stepwise. Okay, the first one is here, oxalic acid. Okay, dissociates into this one, hydrogen oxalate, and then to oxalate. Okay. Now question is to prepare a solution of pH 4.40, and then we start only from this oxalic acid, then we add potassium hydroxide. This is a strong base. Okay, first when it is added, this oxalic acid reacts with hydroxide, okay, and gives this hydrogen oxalate. Okay, and if we add more, and this one is totally consumed, and then this one hydrogen oxalate is it reacts with hydroxide ion to give this oxalate. Yeah, so we have to determine which species are involved. Okay, this one oxalic acid and hydrogen oxalate, or hydrogen oxalate and this one oxalate. Okay, so we have to look at the pK values for this oxalic acid here. pK1 is 1.250. Okay, when you dissolve this one, and the solution is rather strong acid. Okay, because pK1 is very small, and pK2 is 4.266. Okay, so our example is to find pH 4.4. Okay, here, so it is after this pK2, so we know that this species, hydrogen oxalate and oxalate ions are involved. Okay, not oxalic acid, because this pH of 4.4 is way beyond pK1. Okay, it is even beyond pK2. Okay, so we have to use pK2. Yeah, so in order to reach pK2, you have to pass pK1 first. So the first one is to completely completely convert H2OX, yeah, to enough, to make enough hydrogen oxalate. All right, yeah. So first step for us to take is to calculate the number of or volume of potassium hydroxide to completely, okay, convert oxalic acid to hydrogen oxalate. Okay, that's the first step. And second step is that to calculate this potassium hydroxide volume to convert this one to make this one, okay, oxalate, to make a pH 4.40. Okay, let's take a first step. Yeah, so now 3.38 gram of oxalic acid, so we have to calculate the moles of oxalic acid. Okay, what is the molecular weight of oxalic acid here? 90.035. Okay, so 3.38 gram is, yeah, this value, this number is divided by this molecular weight. That's the moles of oxalic acid. Okay, and also that's the moles of potassium hydroxide. Okay, here, and volume is what? We divide by we multiply divided by the concentration. Okay, yeah, look at this one. The volume of KOH is what? Mole of oxalic acid divided by concentration of potassium hydroxide. Okay, this mole, 3.38 divided by 90.035 is 0.03754 moles. Okay, and then divide by the potassium hydroxide molarity, and then we get 46.93 milliliters. Okay, now we have to add more to convert some of it to oxalate. Okay, here is the equation. Okay, and let's say we added X, okay, moles of hydrogen peroxide, the potassium hydroxide, yeah? And then this one hydrogen oxalate is decreased by X, and then this OH minus is completely consumed, and this oxalate ion is moles is equal to X. Okay, yeah. Here we use this Henderson-Hasselbalch equation. Okay, pH so 4.4. Okay, 4.4 equals plus log this one x over this one 0.03754 minus x. Okay, we solve this one for x, and then we get x is 0.02166 mole. Okay, then what's the volume? Here we divide by the concentration of 0.8. All right, and then we get 27.05 milliliters of potassium hydroxide. All right, so initially we already calculated the potassium hydroxide volume, and then we have to add this much. So the total volume of potassium hydroxide is the sum of this volume and this volume, which is 73.98 milliliters. Okay, yeah. So here, so we considered diprotic acid and bases. Okay, and how to make bubbles. Okay? Now we consider polyprotic acid and bases. Okay, to treat our diprotic acid and bases can be extended to polyprotic systems. You see, there are many polyprotic acid. The one good example is phosphoric acid. That is triprotic system. Okay, triprotic system. We have H3A form, which is the fully protonated species, and there is fully deprotonated species, which is A3 minus. Okay, this one. So there are three equations, dissociation equations, first one, second one, third one. Okay, so we write equilibrium constant for each dissociation. Okay, K1, KA1, KA2, KA3. Okay, likewise, if we start A3 minus here, okay, and then we add water. Okay, this is base. There are also 1, 2, 3 equations. For each equation, we write equilibrium constant KB1, KB. I'm sorry, this is KB2 and KB3, and this first one here, and then third one, they are conjugate. Okay, so Ka1 times KB3 equals KW. Likewise, K A2 KB2 times K A2. I'm sorry, this is 2. Okay, it's also equal to KW, and KB1 times KA3 equals KW. Okay, so we can systematically write this one. Okay, so we don't need to actually the dissociation involving this base species, because once we know this the first three information, and then we can automatically calculate these other three. Okay, for base cases. Okay, and then question is how to calculate the pH. All right, and that's quite simple. When we only have initially we have only H3A species, which is the fully protonated species. As in the case of H2A, we take this one as a monoprotic acid. Okay, other forms of species. There are 4 species. This one, and this one, and this one. Right? Okay, and this one could be treated as a monoprotic acid. So we only use Ka1, okay, and then we calculate the proton concentrations by solving the quadratic equation. And likewise, if initially we have only fully deprotonated species, and then we take this one as monobasic species, okay, in this case we take Kb3 here, okay, Kb3, and calculate the proton concentration, okay. Yeah, that's quite simple. But the problem is when we have the intermediate species, you know, unfortunately we have not one but two intermediate species. This one, H2A minus and HA2 minus, okay. Yeah, but we have only one the equation here, okay. How do we calculate the proton concentration? Okay, if we have this initially this species, all right, H2A form, this one, and then which equilibrium constant we use, H2A, yeah, is in between, this one, Ka1A, Ka3. No, H2A, no, I'm sorry, I made a mistake. H2A is in between H3A and HA2 minus, okay? So we use Ka1 and Ka2 only, right? These two. Yeah? The Ka3, yeah? We don't need to consider this Ka3. Yeah? Yeah. All right, so here, in this case, for H2A minus, the proton concentration could be calculated using Ka1, K1, and K2. All right. Likewise, if you have initially Ha2 minus form, this species only, and then what? Look at this one is in between. Which one? H2A, this minus, and H3A minus, okay. So in this case we use Ka2 and Ka3 to calculate the pH, okay, here, right? You understand? So the proton concentration is calculated by using this Ka2 or K2, K3. All right, yeah, that's the idea. Okay, let's do that. Let's take an example of histidine. This is one of our amino acid, yeah, and it dissociates in 1, 2, 3 steps. Okay, first this one. This is a fully protonated histidine form. Yeah, it has two positive charges. Okay, but that doesn't matter actually. And pK1 is 1.6. Okay, when this is dissolved in water, the solution is a rather strongly acid solution, and then this one is further dissociates. Okay, this is A3A form, and this one is A2A minus form, and this one is HA minus 2 minus form, and then this one is further dissociates to the fully dissociated form. Okay, this is A3 minus form. Okay, and for each dissociation, someone already obtained pK values. All right, yeah, let's do that. Yeah, here is an example: a triprotic system. Find the pH of 0.1 molar. This is histidine. Yeah, this is starting species, initial species, and now this is initial, and this is initial, and finally, no. So if we start with different forms of histidine, and what is the concentration? Okay, this is quite simple. First, if we start with this fully protonated form, and it dissociates like that. And then further dissociation, the dissociation is since the pK values are quite different, you don't need to consider. Okay, we only consider this post dissociation, which is K1, okay, and which is 10 to minus 1.6. We solve this quadratic equation, okay, for proton concentration. Quite simple. Okay, proton concentration is 3.9 times 10 to minus 2 molar. So pH equals 1.41. Okay, very simple. And then next one is when we have this one, this first intermediate species initially, okay, and this one, and then we use this equation, and we take only K1 and K2, okay, K1 and K2, because this one species in between. Yeah. So using this K1 and K2, we solve this equation, okay, like that. Okay, this is K1 and K2. Okay, this is K1, and 0.1 is what? Formal concentration of this one, initial concentration of dihydrogen histidine ion, okay? And then we get pH of 3.83, okay? Or, yeah, you may want to use, the extreme case, okay, which is there, what? pH equals 1/2 of the sum of pK1 and pK2, okay, using this one. This is the further approximation, and then we get 3.86. And let's compare this pH value and the this pH value. They are different only by 0.03. Okay, yeah. But I strongly recommend you use this equation, rather complicated equation. Okay, but if you solve the problems, okay, if we practice, after practice, and then this equation will be settled in your brain. Okay. Okay, and next one is the third species. When you initially have only this H histidine form, and then you use which equation? This one. Okay. In this case, using K2 and K3, we can calculate the proton concentration. Okay. Yeah. And then we get 7.62. In this case, although you use, it is a very simplified equation, and then we get the exactly same pH value. All right, but again, if you are not sure, I will strongly recommend that you use this equation, not this extremely simplified equation. Okay. Then finally, we have this one, fully deprotonated histidine. Okay, it reacts with water to take proton from it. Yeah, and then we take this species as if it is monoprotic base. Okay, then we use this equation. In this case, X is the concentration of hydroxide, not proton. Okay, and we solve this one, and X equals 1.37 times 10 to minus 3 molar. Okay, and then pH is given by this proton. This one is proton concentration, which is 11.14. All right, yeah. So now here, from this example, now you know how to calculate pH of solutions which contains initially one of these species. Okay, yeah, nothing special. All right.